Okay, so we are going to discuss Graham's law of effusion, which is another law related to gases, a little more complicated than Dalton's partial pressures. But this law compares the mass of a gas with its velocity. So you'll know, you can understand this concept when you can compare effusion rates of gases based on their molecular mass and do some basic calculations related to this law. So, two terms you need to be familiar with are diffusion and effusion. Really, these are both examples of diffusion, right? And diffusion you've probably heard of before, but that's moving of, actually we've already discussed this in this unit, but that's when gases move from an area of high concentration to an area of low concentration. Effusion is a special example of this where the gas, its movement is controlled by a small opening. So like, if you have a container and you punch a small hole in it, the diffusion rate out of that hole is effusion. So Graham is a scientist that studied these concepts, and he found that gases have different velocities based on their molecular mass. All right, so if you read this chart here, you've got an increasing molecular mass associated with an increased effusion time. All right, now I want you to think about what that means in terms of speed. All right, so if it's taking, so more mass equals more time to effuse. All right, so think about it this way. Let's say all of these gases are trying to go 10 feet. The more the mass of the gas, the more time it takes to go that 10 feet. All right, so more mass means slower. All right. So an example of applying this is, say you have two substances, A and B, that are placed at the end of a glass tube. The vapors of the substances form a solid that is closer to A's end than B's end. What conclusion can be made? All right, so these two gases, when they reach each other, they react and form a solid. So you've got this. Here's kind of a diagram of what's going on here. You've got your tube, and you've got gas A, gas B, all right, A, B, and then after they diffuse through the tube, and when they meet, they form this solid and it winds up being closer to A's end than B's end. All right. So, think about this. From our graph on the last slide, as molecular mass goes up, speed goes down, right? It takes more time for the gas to travel. So which one of these gases is faster? All right, because think about it. What's happening is you've got B is traveling to here, and then A is traveling to there, so which one is moving faster? All right, that's going to be your B, because it goes a lot further before A's, and goes a lot further before catching up to A. All right, so B is faster, which also means B is lighter. All right, so it's got a smaller molecular mass. So that means that choice A would be your right answer, because it's saying that A is the greater molecular mass. So it's going to be the heavier and slower substance as compared to B. So something that we should review is how to calculate a molecular mass. Hopefully you remember how to do this, but what's that handy, table-like diagram with a bunch of elements on it that you're going to be using? All right, have a periodic table handy. And then what you do is based on the formula of your gas. So say you have carbon dioxide, all right? You go to the periodic table, C has a mass of 12, oxygen has a mass of 16. I'm just rounding these to the nearest whole number. That's fine, because I know technically it's like 12.001, and really it's 15.999. So I'm just rounding those to the nearest whole number. And then, based on my formula, I'm going to put in 1 carbon and then 2 oxygens, which will give me 32.44 grams per mole. All right, so you'll have to use a periodic table, keep it handy so that you can calculate these. So, for example, a flask contains 4 gases, CH4, O2, C2H5, and N2. When the stopper is removed from the flask, which gas will dissolve the fastest? Or, I typoed wrong, diffuse the fastest. Alright. So, again, if you remember Graham's law of diffusion, he saw that the heavier the molecular mass, so mass goes up, velocity goes down. All right, the time it takes for it to move increases, so it's going slower. So if you figure out the molecular masses of these 4, the one that is the smallest mass is going to be the one that goes the fastest. All right, so you should see these as your masses of your individual elements, and if you combine these together, you get 16, 32, 27, and 28, which means methane, CH4, is going to be your fastest gas. Okay, so this is the complicated equation for Graham's law of diffusion. So what this means is that the ratio of the velocities of your 2 gases is equal to the ratio of the square root of your 2 gases. All right, so another way you can write this equation, and this might actually be more helpful to you, I just wrote this out this way because this is the way the online course writes it, and you'll see this in your quizzes and stuff like that, but you can also think of this as VB equals the square root, VA over VB equals the square root of mass B divided by the square root of mass A. All right, so the velocity of substance A divided by the velocity of substance B is going to be equal to the square root of mass B divided by the square root of mass A. All right, so let's apply this to a problem. So, which gas effuses 2.39 times slower than nitrogen gas? All right, so we want something where nitrogen gas is 2.39 times faster. So what I'm going to do is I'm going to make 2.39 our velocity of nitrogen. All right, so Vn is 2.39. All right, VB question mark, the gas we don't know, is going to have a velocity of 1 because 2.39 is 2.39 times faster than 1. All right, so if I use letter A in here, if I make that nitrogen, all right, I'll have 2.39 divided by 1 is equal to the square root of some mass divided by the square root of nitrogen gas. Now, something to remember, nitrogen gas is one of those gases that forms diatomic molecules, So the formula for nitrogen gas is actually N2. All right, so that's going to be square root of 28. So from here, now we just got to solve for m, the unknown m. So you know what to do math-wise here. Otherwise, I do kind of just a simple crisscross here so that I can get these guys out of fractions. So I'll have 2.39 times the square root of 28 is equal to 1 times the square root of m, which is essentially just the square root of m. So let me grab my calculator here. If you're using your phone, you gotta flip it sideways. So the square root of 28 is 5.29 times 2.39 gives me 12.65 is equal to 1. And really, I'm just going to rewrite this as the square root of m. And then if I want to unsquare root that, I just have to square both sides. All right, so I'm looking for something that has a mass of approximately 160. All right, so this is where you want to grab a periodic table. All right, we're going to find the masses of these guys when we're looking for one that's going to be 160. So O2 is 2/16, so that's going to be 32. That's not it. Chlorine has a mass of 35, so 2 of those is going to be about 70. That's not it. Bromine has a mass of 80. 80 times 2 is 160. Woo! There we go. So try this one on your own. See if you can come to the right answer. And then start the video back up and see if you got it right. So what is the molar mass of a gas that diffuses 3 times faster than radon? All right, so radon is the slow one, so we're going to make radon 1. So our V of radon is equal 1. Our mass of radon equal to, where is radon? Radon is, wow, big mass, 222. It's all the way on the right side of the periodic table at the end of the noble gases. All right, so let's plug that in. So then our VB, or the other one that we don't know, is going to be 3, because that's going to be 3 times faster. And then we need to solve for mass B. All right, so we're going to have 1 over 3 is equal to the square root of mass over the square root of 222. All right, so we can crisscross applesauce here. So 1 times the square root of 222 is equal to 3 times the square root of m. Square root of 222 is 14.9 equals 3 times the square root of m. I'm going to move the 3 first. All right, so those are going to cancel. So 14.9 divided by 3 is 4.97 equals the square root of m. And then I'm going to square both sides to unsquare root the m. So 4.97 times 4.97 is going to be 24.7, or rounds up to 25 grams per mole. All right, I know these are a little tricky. This definitely looks like a fairly complicated equation, but if you practice this enough, you'll be fine. It's really not that bad.